Hey guys, this is Physics 2.5 through 2.8. We're going to be talking about more about dynamic motion. Specifically, we're going to start working on the concept of acceleration when acceleration is constant. There are times when you might be driving a car, you push the gas pedal down, and you notice your car starts to accelerate or gain speed. Or when you hit the brakes, you slow down. Most of the time in those kinds of situations, the acceleration is changing. In other words, you might start out slowly accelerating as your tires find grip, but then there will be a sweet spot when the amount of acceleration you're getting is the most you can get based on the power of your engine and the grip in your tires. But as your engine starts to rev, there will be a point at which, again, we change gears and we notice our acceleration isn't constant anymore. So because of that, we recognize there is a dynamic acceleration, but we're going to focus on constant acceleration. And what that allows us to calculate. When Newton and other scientists were working with gravity initially, they realized that the acceleration due to gravity, they appeared to be constant, independent of what object was being dropped or thrown. And so they wanted to acknowledge that and understand that better. And so we have this concept that velocity is the change in position over time, and acceleration is the change in velocity over time. Due to that, there are three equations that are going to come out as a product of that understanding. And I'm not going to go through all of the derivations of the equations, but we are going to talk about them. Technically, there's four, and I'm going to rewrite one of these slightly. But you know, these are all for constant acceleration problems. So if you think about an object being thrown through the air, that's a classic example of a problem where we have constant acceleration. Looking real quickly at these three equations, and again, this last one, it just says the average velocity is the average velocity. You add the velocity at the beginning and the end and divide by 2. If you need that information, go ahead and use it, but you guys should be able to find average velocity without a formula. So I'm going to ignore that one. I'm going to talk about these as kinematic equation number 1, kinematic equation number 2, and kinematic equation number 3. This very first equation says that the velocity at the end of an acceleration will equal the beginning velocity. That's what that subscript 0 means. It means not, velocity not, or velocity at time equals 0. So this over here would be final velocity. This would be initial. So the final velocity will equal whatever you started at plus the acceleration, which should be constant, times the time. That's kinematic equation number 1. It's the simplest one of the three. The next equation, I'm going to change this just a little bit. It says that the final position will equal the initial position plus velocity times time plus 1/2 at squared. I don't like this version. It's fine. But in physics, we're constantly determining what we're going to call 0 for a position. I can make 0 not be the ground. I can make 0 be 100 feet in the air. It doesn't matter. So we will make this initial position be 0. But to do that, we have to change this formula just a little bit and make this a delta x. So the formula that I will always use says that the change in position, so assuming we started at 0, it's going to just be that final position. But our change in position will equal the initial velocity times time plus 1/2 times the acceleration times the time squared. If you are a calculus student or someone who's already taken calculus, you learned about taking a derivative. If we were to take the derivative of this equation right here, okay, you would know the exponent of this t is 1. If you're not a calculus student, or you haven't already taken it rather, ignore this. But if you think about taking the 1 from the t down and dropping the t to a 0, the derivative of this would be v naught plus the 2 would drop down, making the 1/2 turn into a 1, and you'd get a t to the first. The derivative of x with respect to time, so that'd be dx over dt, is the definition of velocity. And we notice that it's the first equation. these equations are related to each other through calculus. This is what Newton and Leibniz were after as they worked with calculus. All right, so I'm going to erase that real quick. But the formula that we're going to use, is delta x equals v naught t plus 1/2 at squared. That's kinematic number 2. Our third kinematic says the final velocity squared equals the initial velocity squared plus 2 times the acceleration times, and this is x minus x naught. That's called delta x. So rather than writing x minus x naught, again, we can set the initial position as 0, so it's just delta x is the change in position. I like those versions of the formula better. Now, something special about each of these. There are technically 5 kinematic values. There's v naught, v, a, delta x, and t. Okay? Those are the 5 things. Each of these formulas uses 4 of them. So rather than looking at what they have, maybe we look at what they don't have. For instance, the first formula does not use delta x. So if you're being asked to find the position change, the first equation, equation number 1, is not a good fit. In the second equation, there is not a final velocity. It has the initial, the time, the change in position, and the acceleration, but does not have the final velocity. And the bottom one does not have t. But all of the formulas require the use of a and the use of v naught. If you don't know how fast you are moving to start with, and you don't know how much you're accelerating by, kinematics can't really help you. Those are things that you have to have, or they have to be what you're looking for when you work with a kinematic formula. The algebra behind these is actually pretty simple, and we can use 2 or 3 of these equations in the same problem to help simplify or solve a problem. And you'll see that going on. Right here is kind of a quick problem-solving concept box. It gives you sort of some steps to work on. You're going to need to write down your knowns, draw diagrams. Diagrams are so helpful. Understand the relationship between different things. Things like the word at rest means initially it maybe didn't have a velocity, or that's how it ended, had 0. Things that are objects falling through space are going to fall due to gravity, which has a set value. These problems are all solvable as we contemplate what we do know and what do we need to know. So working with Galileo, who did a lot of work with understanding physics and understanding the basic motion of a lot of stuff, one of the things he worked on was falling objects. And this concept that in an air-filled tube versus an evacuated tube, we could get objects to fall at the same rate. In other words, that gravity is independent of mass, or that the gravity between 2 objects here on Earth is independent of the mass of that object. So it will fall, I would fall at the same rate that a feather would fall if we didn't have air resistance to slow us down. Specifically here on Earth, the number that we're going to use to approximate gravity is going to be 9.8 meters per second squared is the acceleration due to gravity. You will see the little g get used to represent gravity all the time. But it's an acceleration, so we need to remember that. It's not a velocity, it's an acceleration. We can indicate that by the fact that it is seconds squared in the denominator. So when we drop any object off of a building, we'd expect it to fall at 9.8 meters per second squared, minus any air resistance. And that's something that we would look at a little bit more as we go on. A couple of things about objects flying through the air. You may or may not have noticed, but this formula right here, okay, v naught t plus 1/2 at squared, that formula is a quadratic based around time, which means if I use time as my x-axis, okay, the position of the function will follow a projectile path or a parabolic path. So if you understand a lot about parabolas, you would understand things like this is the vertex, the maximum, and that it's symmetric about that, meaning the time going up and the time falling down should match. If I throw an object up in the air, all of the properties on the way up will be mimicked on the way back down. And those are important concepts. The last thing that we're going to talk about is understanding that the slope of a curve, if I were to model, and we'll do this in class, but if I were to model velocity versus time, okay, in a graph, say here's the velocity at different times, at 1 second, at 2 seconds, and so on, the slope of the equation is the change in y over, let me grab my other pen, over the change in x. Well, if we're taking the change in velocity over the change in time, then the slope in this problem, in this green diagram, would actually be the acceleration. Over here, we have position versus time. Well, the change in position over change in time, that is by definition the velocity. So when we look at these examples of position versus time or velocity versus time graphs, the slope gives us a ton of information. And this is why calculus gives us that step where we can get instantaneous velocities and instantaneous accelerations. Those of you who are in calculus and have done derivatives and understand what derivatives are, that's awesome. The other thing that we can do is we can do area under a curve, something that we'll talk a little bit more about. But area under a curve has meaning based on the measurements we're using. Okay, good luck, guys. Hopefully this helps you with the information that you need in chapter 2 to finish up the homework. We'll see you in class, and good luck.